So this topic that I'll be presenting was an internship project of Shin Chin when she came to visit us last summer. Jyotirmoy Deshmukh is her advisor at USC, and Andrew Best is my colleague at Toyota Research Institute. This is part of a broader effort. We have a preprint of our current efforts here at the archive. Of course, we'll be submitting an extended summary to NSV. So basically, the idea that we want is to have a controllable AI that we can use to probe the weaknesses of a system that we have designed, in that case, an autonomous vehicle. We want to have a controllable AI that we can deploy in simulation to stress test. In this case, that takes the form of an adversarial agent that can automatically learn to cause the autonomous driving. However, it's not interesting if this AI is just maximally evil, if it barrels down the freeway the wrong way, trying to hit everything that it encounters. Instead, what we want to do is we want to have it respect rules chosen from hierarchical rulebooks. This term hierarchical rulebooks is a term that comes from Newtonomy. They explore this idea in the context of safety rules that we would want for autonomous vehicles in terms of having a hierarchy of having it follow traffic rules, comfort rules, and regional culture conventions. But in this case, we turn it around and say that those are the constraints that we want this adversarial agent to follow, while also finding failure modes. So we're provisionally calling these logical scaffolds. They're sort of logical structures around which the AI grows and becomes stronger. So the idea is that we kind of bridge the gap between the logicist approach to AI and the connectionist approach to AI by letting each of them do what it does best. So the logical structures provide targets and constraints, but the neural structures allow it to learn to generalize and to have flexibility in the ways that it pursues its objectives. So the problem statement is that we have some scenario. For example, the ego vehicle must follow a lead car on the freeway, or there is a lead vehicle, which is the adversarial agent, and the ego vehicle approaching intersection that currently has a yellow light. And we have a target specification, such as make the ego rear end you or make the ego run a red light. So I should explain a Toyotaism here, which is that when we say ego, we mean the device under test. The ego is the autonomous driving stack, which was developed, and we are trying to stress test it. So the logical scaffolds constrain the allowed behavior. For example, in both of these, well, in the make the ego rear end you, it could be easily satisfied by just driving backwards. And the intelligent agent should find a case where the ego fails to maintain its own specification of not rear-ending things or not running red lights while respecting its own constraints. So the way that we structure the solution is with reinforcement learning. Shin, during her internship, developed a tabular reinforcement learning agent and also a neural network. As she was developing the tabular network, she was bounding with excitement to abandon it and start the neural network. So, I mean, it's what's cool these days. So she was very excited to get to do the neural network, and we represent the logical scaffolds as signal temporal logic formulas, and we have some implementations. um, in PyTrees, PyTorch, and some simulators. So signal temporal logic is a logic that talks about signals. The logic does formally define what a signal is, but for explanatory purposes, we can think of signals as functions that evolve over time. And then these signals, we can apply functions to them, and we can insert them into predicates of different types, such as inequalities. We have the usual Boolean operators: conjunction, disjunction, negation, implication. And then we introduce temporal operators, temporal operators, always, eventually, and until. So some example of automotive formulas that we use in signal temporal logic is, for example, always stay in your lane. And that's accomplished by saying that X, the position of the vehicle, must be between the lane marking and some margin, and on the other side from the other lane marking plus its margin. And we add an always operator to say that this should always happen over time. We can express more complicated things, such as if we have a signal that expresses whether the brake is active, and it's a 1 if the brake is in fact active, and a 0 if it's not active. We can say if the driver presses the brake pedal, then eventually, after at most 0.1 seconds, I apply deceleration. So eventually can be indexed by a time interval over which it holds. The acceleration of the actual vehicle must become a deceleration. So this is, for example, a specification for the controller that is monitoring the brake-by-wire signals and choosing, how to actually control the vehicle. So we would want him to actually decelerate when the driver requests a deceleration. So what's kind of interesting about this signal temporal logic is that we can give it Boolean and quantitative semantics. So Boolean is just the question of, is the property true at each point in time? But the quantitative semantics is, how true is the property? So we have this notion of robust satisfaction. And the way we calculate robust satisfaction is by induction on the structure of the formula. So for the case of these simple predicates with inequalities, we calculate the robustness by subtracting the two sides. So if I have f of s less than c as my formula, then the difference between f of s and c would be the robustness. In other words, how close am I from violating this predicate? And that will give me the robustness. If I have Boolean operators, such as conjunction, then the robustness of the conjunction is the robustness of the one that is closest to being violated. So it's the minimum of the robustness of the two conjuncts. Similarly, for disjunction, it's the maximum, and for negation, it's the negative. Implication is more complicated. What we do in that case is there's an identity in logic that allows you to unpack A implies B as not A or B. I hope that's correct. And then we just unpack as the robustness of disjunction and negation as appropriate. Okay, so until is more complicated. For the moment, we don't have until in our toolchain, but it's also possible. So what's interesting about signal temporal logic is that it's very convenient for folks who don't have a rigorous training in formal methods, such as the engineers at Toyota that we work with. It's quite natural for them to write specifications like this, like drive-in lane means, this is actual executable Python code, by the way. So left lane boundary plus margin should be less than or equal to your lateral position minus half the car width, and your lateral position plus I have the car width should be less than or equal to the right lane boundary minus the margin. And then we just add an always operator to it. And given a trace, so this little picture here that I have, these dotted lines are the lane boundary, and these red lines are the margin. Given a trace of this car that is initially drunk and then he sobers up as time goes by, it's very easy just by implementing the semantics of the different operators that I described, the always and the conjunction, to just at each point in time say what is the robustness. And so here we see that at each point, at the beginning, he's kind of drunk and then he sobers up, which is what we would expect to be the case. So so then it's very painless for an engineer who doesn't have a background in logic to quickly spin up these types of specifications and have something that works quite nicely. So in fact, it's commonly used at Toyota. So this is some older work from some folks from a different lab. Actually, Joe Deshmukh is a co-author on this work. He previously had some work on mining requirements from closed loop models. So if the engineer who knew how your signature piece of technology works retired and now you don't know what the specifications are, he had some work on mining the requirements or extracting them. There's also there's plenty of work on sort of robust monitoring, on efficient monitoring. Here's another plug for my own work on backpropagation for parametric STL, which is this idea that the parse tree for a signal temporal logic formula actually bears a striking resemblance to the computation graphs that libraries such as PyTorch and TensorFlow use. And so then we can use that relationship if we replace the robustness function with something that is differentiable at each point. Then we can use just these off-the-shelf ML libraries to learn parameters of logical formulas. So now I'll just briefly talk about reinforcement learning. Reinforcement learning is this idea that some agent is dropped into some world that it doesn't understand, and it has to learn to interact with that world through three signals. There is an action signal that it submits to the world, and there is a reward and a state signal that it gets back from the environment. And this state, in our case, is actually not necessarily a complete description of the world, because our adversarial agent doesn't actually know, for example, the state of the internal states of the device under test. So in general, we can think of this state really as just being an observation. It's not necessarily a Markov state. And the hope is that over time, the agent will learn to maximize reward from its just interactions of submitting an action and observing back rewards and states. So there's a specific algorithm called a deep Q learning network. And what that is essentially applying an update rule. So this update rule that I have is not the deep Q learning update. It's just the standard Q learning update. I included that one instead because it's a little bit easier to wrap one's heads around. So the idea is that at each state, and where a state in this case is described as the velocity of the cars and distances of the cars to each other, and in the case of the traffic light, also the distance to the traffic light and the state of the traffic light, whether it's yellow or red. And that is fed to a neural network, and the neural network outputs a vector of so-called action qualities. So for each of the possible actions, it gives them a quality rating. So in this case, what we do, both of the case studies that I described are there's only one action, which is acceleration. So we discretize the action space, a few discrete accelerations that the agent may take. And so the neural network outputs for each of these discrete accelerations, for example, -0.1, -0.2, -0.3, -0.5, and then out to the positive side, 0.1, 0.2, 0.3, 0.4, etc., outputs a score on what it thinks is the best quality action at that observation. And then based on those actions, submits an action to the simulator. And then based on the logical scaffolds that may be active in that case, it receives a reward. So for example, if it attained its objective of causing the ego vehicle to run a red light, then it gets a large, it may have won the game, but it gets a large positive reward. But then we also evaluate the constraints, which are, is it driving backwards? And if so, it incurs a negative reward for that, right? Based on the robustness of the formula. If it's very negative, then that corresponds to a much larger penalty. If it's only slightly negative, then maybe we give it a smaller penalty. Now there is a relative weighting issue here in the reward, which we hope to systematize in the future, but currently the rewards chosen here, I mean the weighting of the reward signals is currently tuned as hyperparameters, but we hope to eventually systematize that weighting. Anyway, so this Q update function just summarized sort of how that update is performed. So at each time step, at the state and action that we're considering, he updates this is how he learns. So basically, suppose he already took an action, and at the beginning of that time step, it was time t. So at state t and action t, he updates that value by adding onto that. Alpha is some learning rate. He has, at the end of this loop, observed some reward. And then there's this part where he looks at he looks at the maximum of the actions. So at the new time step at which he arrived, so this is t+1, and it's discounted because reinforcement learning assumes that the future is a little bit discounted. So basically, this is at the new state the best sort of quality available, right? So he took some action at time t, then he looks at the reward that he got plus what is the best thing that's available going forward, and he sees the difference between this sort of experienced reward plus discounted quality, and he sees how that was different from his original expectation. So this is his reward signal, and this learning rate tells him how much he should update that sort of belief. So as I mentioned, this is the tabular version of the formula. In the neural network version, there's additionally a gradient in terms of the neural network parameters, which complicates the treatment slightly, but it still works as expected. So we have an internal simulator that we use, but there's a Carla implementation that she also used for research publication purposes. So she has the single lane following. I'm missing the yellow light controller here. I just realized. So I will update these slides before I share them with Sridhar. And she also, I forgot, she also has this lateral control case study. So basically, in this one, since I haven't described it, basically the blue car is the adversarial agent, and the red car is the device under test. And the goal is that the blue car should complete a lane change such that the red car hits it, and the constraint that we have is that it should not sort of barrel into the red car. We have this requirement that whenever he merges in front of the red car, there must be a minimum sort of time gap that of reasonableness. And so any defect that the red car has is not because the blue car was unreasonably cutting it close, but actually because there's a defect in the red car that it doesn't do a good job. Due to the time constraints of Shin's internship, we weren't able to apply this to the TRI autonomy stack, but the preprint that I linked to earlier on has a implementation in terms of a simplified ego controller. So philosophically, what we have is there's the logic layer initially specifies what the agent should do, but not how it should do it. And then the nature of signal temporal logic lets us automatically monitor that it is being done, or with what quality it is being done at each time step. And then we use reinforcement learning to sort of figure it out just by experience with the environment, agents that learn how to do what is required. And in this case, what is required is to stress test the device under test subject to constraints of reasonableness. So the future is that we want to build an evil AI and hire it as a consultant. Currently, we have DQN, but we want to build this out into a fuller tool. Oh, we're calling the tool Loki, by the way. I just realized this is the first time I told you about it. So it's kind of this little demon that does useful things, hopefully. And it should have a bank of algorithms that it tries and selects the one that seems to be performing best on that particular scenario. I mean, reinforcement learning is a rich field, and it has a number of algorithms other than DQN. And some things that we want to investigate is if we build an agent that is adversarial for, let's say, V version 42 of the autonomous driving stack, how can we use that to warm start an adversary for version 43 of the driving stack? And another thing is composability of agents across scenarios. So if we have an agent that is really good at executing malicious lane changes, and an agent that is really good at making the device under test run a red light when it was initially yellow, then when we compose them, do we get something interesting? And the idea there is to instead of sort of building up very complex scenarios with a bunch of different malicious agents, can we sort of decompose that to a few agents that then sort of get composed in interesting and reusable ways? So Shin, after her internship, has been working on integrating the Carlos simulator and OpenPilot for further development. It seems like there will soon be, I heard there was some news from both Carla and OpenPilot. Apparently there's going to be a default integration that they provide. So that will be an interesting way to test out future work. And with that, I open it up to questions.